Good morning and welcome to the next edition of Ganesh.tech. We all know that there's a buzz in the air in India that chips are going to be manufactured in India and our economy is going to boom and we're going to be the next electronic superpower in the world and things like that. Many things come out on social media and all that. But that's not that's being too simplistic. From the chip, the ability to make a chip, till the time it gets into a device where you can communicate or use it for any purpose, as a router or in a computer or in your mobile or any application, whether it's military or civil, a lot of steps, a lot of intermediate expertises. It takes a long time. So today we're going to talk about all this. What are the steps in between? What does it take for us to convert the impending chip manufacture in India into something tangible for India and to become an exporter of electronic hardware in the world? For this, I have with me Vijay, who's going to take us through all the steps. Right. Vijay, welcome. How are you and how are things?
Hi, Dad. I'm good. How are you? Things are well here.
I'm fine. Oh, good. It's good to know that. So we're talking about the, buzz in the air about chips being manufactured in India and how India's economy is going to take off and all that. So, what are your initial view ideas on that?
I think manufacturing chips is probably one of the hardest things you end up doing when it comes to establishing an industry around computers and software. By no means is it a trivial endeavor. So it's great to see India embark on this path. So I'll just put that out there. It is just invigorating and fascinating. I'm sure it'll offer a lot of employment, not just now, hopefully in the years to come, if this becomes a nice virtuous cycle. And it will definitely open up not just the computer industry, but industries across the board, from manufacturing to aviation. It will just expose the domestic supply chain to a more ready supply of domestically manufactured chips. It won't happen overnight. These things take time. Like I said, it's one of the hardest things you can do in building a computer. But at least now, hopefully, it will be one more option that we can consider. Uh, any industry can consider in India when trying to bootstrap their electronics or computing systems.
Fine. That's a nice opening. Uh, First, I want to discuss what is the process involved in the chip making itself. You see, a lot of people think chips are something you just make overnight. You put up a factory and or a fab, as it is
Yeah.
called, at start off. But it isn't so easy, isn't it? There are various parts before you can make a chip. There are various issues before you make a chip. I mean, let me highlight what I know, and then you can add on. To the best of my understanding, uh, the design of a chip, right, is made in X place, and that today happens to be USA. It's not only design of the chip; it's also the design of the process of making the chip. The whole story is made in USA at this point of time. I think USA controls everything. Then this machines to make the chip, which is called the lithographic machines. These which have the capability of making these wafer thin chips,
Yeah.
like the 5 nanometer, which is the latest one on a fab. And then what people are looking at is the 3 nanometer one.
Hmm.
Those designs of the lithography are made in Netherlands at
Yeah.
ASML. And finally, based on the design of the chip and the chip making, you know,
Machines.
lithographic machines,
Yeah.
the entire chip is fabricated in, a place like Taiwan or even China, even Korea makes it.
Yeah.
But right, so it's a third. So someone has to have a fab.
Yeah.
So it is these three things which give you the capability of being a chip manufacturing giant.
Yeah.
And the way I also look at it is that today, irrespective of what Taiwan has capability as, which is much spoken of, it is a combination of these three entities which give the capability of making chips, and which China is trying very hard and not been able to come to that level. Right, that's the first part. The second part is that besides America,
Hmm.
I suppose Taiwan, China, Korea, and to some extent maybe even Japan and some European countries have the capability of making chips. It's not as if they can't; they can, and they might not be able to make all 5 nanometer chips, but 9 nanometer and all that they can
Yeah.
easily make. That's one. The third point I want to make is that you don't always need 5 nanometer chips or high end chips in most of your cases. In most of your use cases, you need simple chips, maybe even 2 generations old or 3 generations old, to run your system.
Yeah.
And ultimately, it depends on what you want to run in that system,
Yeah.
right? So, am I right in this, or you could just elaborate a few more issues on this, and then we'll take it further.
I think you in your first point you broadly covered no, in your first 2 points you broadly covered the ins and outs at a very high level, the manufacturing players, pieces, economies that go into fabricating a chip. So it's not just the actual fab, it's the lithography, it's the chip design. You're absolutely right. I don't have anything else to add there. Uh, your third point is probably more interesting to me, and it is also something worth understanding in greater detail because y the point that you made was that you don't necessarily need the 5 nanometer variety always. When you said that, I recall a conversation I once had with a engineer at NASA who was a software engineer on the Voyager probe. Voyager 1 and Voyager 2, they're probably the most uh, impressive, inventions of humanity. They've gone farthest, that we have sent any object out into space. Uh, I'm not sure whether they're still sending us data. I think they might be. The fact that they have this level of longevity beyond their prescribed mission lifetime is a testament to innovation in engineering. The interesting thing that he said back then to me was, even the Voyager will have has chips.
Yeah.
It's an onboard computer to collect the data, send that data back. And when I say data, it has a whole bunch of instruments, scientific instruments from where it is collecting bits of information and sending it back to Earth. And the thing that he said to me back then was it was a very simple system. Like in terms of software, it's nothing compared to what we see today. It basically has a few, I'm going to use a few technical terms, but really it has a few interrupts. And based on when those interrupts are firing, a few things end up happening. So you can almost think of this as a very, very mechanical system. It is a digital software system, but it almost borderlines in its simplicity and starts to resemble with a mechanical system, like almost like a bicycle. So simple things, simple chips can first of all tend to have a long lifetime, and they can do interesting things if you deploy them in interesting ways. So that's just an anecdote I thought I would call out. And you're absolutely right. We don't have to chase. No one has to chase when they start out with chip manufacturing after the 5 nanometer chip design. You can start out very, very basic and then build your way up to more sophisticated manufacturing and fabrication processes.
Yeah, just to put things in picture, The Voyager 1 and 2 were launched in 1977.
Right.
Okay. And as per the mission status, it has done, the mission elapsed time is 46 years, 4 months, 15 days, 15 hours, and 44 minutes at this point of time.
Yeah.
So it's a long time back,
Yeah.
and it's gone, God knows, I mean, how many miles. Let me read that out also. At this point of time, it is the distance from Earth is 15150,106,782 miles. I mean, that should be somewhere around 15 billion miles away from Earth, and it's still sending data.
It's still sending data.
Yeah.
That,
So it just goes to prove that you don't need the latest. In 77, there were no chips of this variety. There were more mechanical versions, right? I just want to tell everyone 77 is the year I got commissioned. Okay. Uh, and with that, you're able to do everything. Okay. And so you don't need the latest chips. You just underscored my issue. You need some capability. You need some, you need to understand what you want. Okay. And you need to put that in picture, and that's when we'll become atmanirbhar or indigenous from an Indian viewpoint. Yeah.
yeah.
So I just thought I'll put this. Yeah, you just carry on with the next story you have on this.
Yeah. So that's absolutely right. And it's also important to understand that the chip manufacturing and fabrication innovation space, like this didn't happen overnight. Humanity, like countries all over the world, we have been at it for a while now. So especially with India thinking about and Indian manufacturers thinking about setting up manufacturing plants, fabrication plants to develop chips in India, that is great. But to me, that is already a breakthrough. Like if you're able to produce some chips, that's already a breakthrough. And patience is probably a virtue here. Things will happen as long as you continue to be at it. But chips and manufacturing of chips and fabrication of these sophisticated devices is just one aspect. Even after you put it on a motherboard in a CPU or a computer or your mobile device, that is not the end. And probably that is what I want to talk about. And this is the part uh, I feel is lesser appreciated. We assume that there'll be a chip and someone will write code for it and it'll all be done. Uh, we don't often think about all the different steps involved, the layers involved in getting programmers to develop apps that ultimately work on the chips that people end up manufacturing, whether they are in your mobile devices or they are in your refrigerators, like that, or in your remote controls or in your routers. That is a later, like that's a different conversation as to where they end up. No matter where they end up, there is always some set of things that you need to line up for that code to actually work on the chip. So I thought I'd just go through that entire list. Again, it's
So
simply,
at the outset, how many steps are there? Just to give a broad idea before you.
if you want to go all the way to something like creating a mobile application that is coming out of your fab, like as you on the software side of things, at least there are about 7 steps involved. uh,
Okay.
right, and you can knock out a few things here and there. A few of those layers can be reapplied again and again. Like once you've invented them, once you have developed expertise in them, it applies more broadly. But almost some element of all of those layers of expertise end up getting used in getting that mobile application to work successfully on a chip.
So okay. So you're going to take us through that.
Yeah, we
Yeah.
can go through that list together. Yep.
Okay. We'll go through that list. So you have a presentation, and here it is.
Yeah. And it's a very simple presentation. There are not too many technical things going on here. I'll go from the bottom. So if at the very bottom you can see a chip, and I've tried to keep things very simple. And on the left hand side you have the chip. On the right hand side there is a representation of what is actually running on the chip, right? So you have zeros and ones literally running on the chip, and these zeros and ones, are representations of actual electrical, pulses going through the digital circuitry, the electronic circuitry on the chip. But the chip really understands only zeros and ones. That is important to, wrap your head around. But you and I, if you're going to go and write an application, it doesn't matter for what device, mobile phone or refrigerator, we are not going to go start writing zeros and ones on a blackboard and flash that onto the chip. Instead, again, this is way back in the day, uh, probably around the 70s, when people realized that instead of doing that, did the next slide come through?
Yeah, it's there.
Okay. So the next thing that you really need is a chip architecture. And when I say chip architecture can mean many different things, but from a software standpoint, the most important thing is something known as the instruction set or the execution instruction set. Uh, these are nothing but mnemonics for these zeros and ones. So instead of putting down individual zeros and ones, you have instructions, you have arithmetic instructions, you have control instructions that tell the, you know arithmetic unit on board, the logic unit on board, the these days you have units for every single thing. You have units for speech processing, you have units for machine learning, audio processing, whatnot, and all of them will come with their own instruction sets. And the instruction set basically is a slightly, just above the zeros and one layer. It's basically giving you a very primitive set of instructions that you as a human being can read a little better than just raw zeros and ones. uh, but there is almost a one-to-one relationship between what is happening on an add instruction and how it gets translated to zeros and ones. That is a very, very small jump, but it was an important jump because it reduced a lot of time for human beings to, not deal with zeros and ones, but instead deal with these mnemonics.
Okay.
The
So
Yeah.
yeah, go ahead.
The next thing is you have a compiler. What's a compiler? uh, Long ago, a professor of mine told me that whenever you set up a chip manufacturing company, you know the first thing you need to do is you need to go hire compiler experts. Compilers are pieces of software that take code. As we all know, like programmers write code, right? But you need something that takes that code and translates it to these zeros and ones, and it does so through this instruction set, this chip architecture in between. So a compiler will take a piece of program or code written by a human engineer, and it will basically start forming flow charts. It will try to understand how that code executes instructions one after the other, and then tries to optimize the way those instructions are executed, tries to save the time involved in executing those instructions, and organizes that code in a way that so that it can run faster, take less memory, and more importantly, it takes human written code and translates it to machine understandable code. So it will take human written code that is more familiar to programmers, and it will translate it to these move, add, subtract, jump instructions, which ultimately get easily translated to zeros and ones. So that is the layer above it. And this is where we start getting into interesting complexities. Compilers are also closely related to the next layer above this, which is programming languages. Uh, Software engineers understand programming languages. They're not thinking about the compiler. But when you think about a compiler, the compiler that you have is designed typically to take code written in one specific programming language and translate it to code that a specific chip architecture can understand. Now we have gotten sophisticated about this as well, where we can, we have compilers that are quote unquote multilingual. They can understand programming languages, multiple programming languages, and they can translate it to machine code that can run on different chipsets, different architectures. And there is a lot of innovation happening in this space. Programming languages, I don't know if you've heard of things like JavaScript or C Sharp or C. Uh, like those are good examples of programming languages, and these are things that you learn in school. These are things that you learn in universities when you're doing a degree in computer science or software engineering. So this is, and as a software engineer, this is my bread and butter. This is what I routinely deal with. I don't deal with the compiler too much. I don't deal with the chip architecture. I don't deal with the chip. But understanding those fundamentals is important to then understand how a programming language is designed and what it can allow me to do or what it will prevent me from doing when I write my code. And so that gets us to, the next layer, which is the actual code. This is the actual code that I can write. Here I'm giving you a very simple snippet of a for loop. This loop is doing nothing but going around 10 times, printing the numbers from 0 to 9. And this is just a simple example. At this point, I can easily say that it is this English like script, where you have words like for and print that get translated all the way down to move and jump and add and subtract instructions using the compiler, and then that ultimately gets translated to zeros and ones that can actually run on the chip. You So easily we can see, just a simple block of code, you need all of these expertise. You need expertise in how you design a programming language. You need expertise in how you write that compiler. That compiler needs to understand the programming language design and the chip architecture, and the chip architecture needs to translate well over to the chip itself so that the zeros and ones can fire properly. So already we are seeing some interesting complexity here. But programming today is not as simple as printing out numbers from 0 to 9. It's gotten a lot more complicated. So the first thing you need to think about when you're programming is, what is the operating environment in which your code is going to run? Is it going to run in an operating system? Like, will it run on a mobile device like iOS, Android? Will it run on a desktop, Windows, Mac OS? Will it run in a server somewhere like a Linux server? Or is it going to be a web application that it will run in a browser like Chrome, Safari, or Firefox? So your code is not living in isolation. Your code is always living in an environment. And these are the popular environments that we know of. Like I said, you have code in refrigerators as well. You'll be surprised to know that there are some high-end, high-tech refrigerators that actually run entire Linux or Windows operating systems, so your code very well could run in them. But you also have simpler coding environments or operating environments that these refrigerators and air conditioners tend to support, and you have to go write code for them as well. So again, the examples that I'm calling out here on the right are very, very simple, basic, well known, but the ecosystem is much larger than what I'm representing here in my slides. Then, you know what has happened over the past, I guess, 20 years is that people realize that once you've written a piece of code, you can start reusing it as building blocks almost in larger and larger projects. So it makes little sense for you to start from scratch every single time. As a result, people, companies, enterprises, organizations, the open source movement, all of this pushed us in a place where you are almost never starting from scratch. You are starting from typically you're starting from something known as a software development kit. Which is nothing, it's just a fancy way of saying that there's a package of pre-written code available for you, and you can just work against that. So really, most of the time, engineers like myself, when we do our day job, we are working against established software development kits to do our work. Popular ones include, the Java development kit, the JDK. You use this to write Java programs, or you have UI kit, or the Android SDK. UI kit is used for writing uh, iPhone applications, and Android SDK, as the name suggests, is used for writing Android apps. So these software development kits really give you rocket boosters in terms of productivity in getting a lot of work done, and really help you to write very, very sophisticated pieces of software that we have all come to know and call as apps or applications. So you can write mobile applications, or write a web application, or a simple website, write applications for operating systems like Mac, Windows, Linux, very, very easily with the help of these software development kits. And this really represents to me, there could be other ways of looking at it, but to me this really represents the entire different layers of uh, the software economy or the coding economy, as I come to view it. When you write an application, uh, you're typically working against a software development kit that is working in a predefined operating environment. You're writing code when you're building out your application. For You write that code in a programming language that someone has designed. That programming language is set up to work within the confines of a compiler. That compiler takes your code in that programming language, translates it to an instruction set prescribed by a chip architecture, and that chip architecture, and those instructions are easily translatable down to zeros and ones in the chip. So, and you need expertise in all of them. And one of the
So
things that anyone should be asking, now that India is going to embark on manufacturing chips, is where are we in terms of expertise, real expertise in each of these layers? It's not just about app development.
yeah, so let me ask you that question: where are we? I mean, in your assessment.
um I would say that we are great when it comes to building apps. A lot of our homegrown companies have demonstrated that. There's no doubt about that. We are really, really good at building apps. We are really good at building software development kits as well. We're really good at writing code. But can we actually say that there is a Indian startup or an Indian company that really owns a platform, like owns a operating system, uh, works on an operating system, develops an operating system? There is no doubt that there are experts out there in India who are experts in the Android operating system. It's an open source operating system, of course, so people would have gone and dug deep into it. There are similarly, Linux is open source, so like, not only am I sure, I know for a fact that a lot of contributors from India contribute to Linux. Similarly, Chrome is based on open source technology, so is Firefox and Safari. So there is no dearth of expertise. But to me, the missing piece in all of this is that there is no commercial entity that has taken these open source stacks of technology and turned it into a viable business model, to the tune that, say, a company like Apple has done with iOS, or Microsoft has done with Windows, or Google has done with Android. So it'll be interesting to see in the future if something of that nature shows up. I also wonder sometimes about you know expertise in programming languages. It's not always clear. Again, we have great coders. India produces a lot of brilliant coders, myself not included. I don't count myself as a great coder. I'm okay. But I've seen some of the smarts that come out of Indian universities, and it's just amazing. What I haven't seen is a lot of innovation in programming language design. I have typically seen that being confined to universities in Europe or North America. It is, if we are going to embark on a serious adventure on chip manufacturing, I think it would be prudent to also embark on a serious adventure in thinking about programming, language design, and invention. It is, I reject the notion that the latest and greatest in programming language design is the best that we can do. There is nothing more to innovate. No, there is a lot to innovate in the space of programming language design. Similarly with compilers. Compilers to me are, again, an interesting area. They're closely related to programming language design. And again, I'm sure that there are experts in the existing compiler systems that are open sourced and available to everyone. But I don't know if there is real innovation happening, real research happening in the space of how do you write an optimizing compiler. Uh, and then of course you have chip architectures and the actual chip design in the just in the by the process of manufacturing something, you will start thinking about that. But
Right.
that is my take.
Yeah. So you laid out all these 7 layers. You have the You're getting into the bottom layer. You have a capability at the top layer of writing apps and all that, but the
Yeah,
in between layers are missing, isn't it? So, and those, I wouldn't say missing. You don't have
yeah.
that the expertise so far.
we
So it's
we haven't
important.
we haven't needed to build that
Yeah,
expertise.
I agree with you. But if you want to be independent, you want to be Atmanirbhar, and especially for military applications where you have to be absolutely foolproof and you security is of very high requirement of your, where your data has to be absolutely secure and sanitized at all given times. So you have to go through this entire loop of yours, the 7 layers, to
Yeah,
make it happen for yourself,
yeah.
right? So to that extent, I mean, this is my view that it needs a government push to get this going. Otherwise, it will not happen.
I completely agree. And on the notion of security, you're absolutely right. We always think of security and cybersecurity or privacy issues or privacy leaks, data leaks, in abstract terms. But really, what it comes down to is a software bug, a software bug that caused the wrong thing to be written in the wrong place that was easily accessible to someone, a password that should have been encrypted but wasn't. And a lot of times, these bugs take the form of very unexpected shapes and sizes. If you're I can't tell you the number of times I've been caught off guard by a bug in the compiler that I would normally take for granted. And that gave me headaches for a few days until I realized that, oh no, the issues with the compiler, I probably need to either upgrade to a newer version or go back to an older version. If you don't understand, and if you don't educate students, and if you don't build out research capabilities in the universities today in these things, 20 years from now, I honestly don't think that the chip manufacturing to make, okay, let me put it this way, to sustain the chip manufacturing industry in India, you need to start thinking about building in-house academic capabilities for all of these things, especially the layers in the middle, especially around programming language design and compilers. And you're right, the government can play a big role here. And the best way to start playing a big role is to start giving out research grants. And those research grants should be targeted towards how to build academic curriculum in teaching students, but also spending those research rupees in terms of actual research, innovating, publishing peer-reviewed papers and publications, uh, putting your ideas out there, testing them with the community, with the international community, and developing confidence and expertise in what works and what doesn't in an Indian context.
Yeah, thanks. I think you today laid out a whole lot of things. I do hope someone up the chain listens to this and will see how I can put it across to them. So it's not important that you can make chips. You have to make them work for you.
Yeah,
You have to make them work for you, and to make them work for you, you need a whole lot of academic rigor. And once you have that academic rigor to make things work for you, then you need the business acumen to design everything, and then it is only then that you'll get the full value of this chain from bottom to the top. So there's a long way to go from you know chip to the ultimate software which you see on your mobile,
yeah,
right? With this, I think we've done for the day, and this topic will come back.
yeah.
Now that we've seen the layers in this thing, are there any layers for the hardware also, which we have to go through?
There almost certainly are.
Yeah,
I'll just call out probably the biggest layer in hardware that I can think of. Well, when I think of hardware, I'm also thinking about networking. I'm thinking about how you establish complex channels of actual communication that is able to hook up multiple of these machines together and code deployed across multiple machines and make all of them sing together. The thing I will leave you with is there are very few companies in the world, there are very few entities and organizations or companies in the world that are vertically integrated across the stack. And those entities and organizations and companies have the capability to build their own data centers. If you
okay,
want to build your own data center, first of all, you need to be vertically integrated with expertise across the software stack, not just chip manufacturing. And then you need to figure out the networking aspect, which is the
okay.
communications aspect.
So yeah, so that means you actually need the chip manufacturing capability, then the ability to have the software stack, and then the ability to put all this hardware together in the form of a network with machines wherever they are in the form of where they are. It's not important to have the latest chip as much as to have the capability in all those,
Yeah.
right? So I think you made the larger point well. Thanks a lot. It was great talking to you on this. At least I've learned something new that the chip doesn't matter. Otherwise, it just remains a potato chip. If you need a semiconductor chip, you need to do much more with it, and you need to have much more ideas about it.
The
Right.
chip is super important. I just want to reiterate, like, I'm not the expert, I'm not the hardware person. Like, my expertise lies in software, but I am very aware of how hard it is to design, fabricate, and manufacture chips at scale. It is not easy or trivial at all. I'm just trying to highlight that there is so much more, and
More
what I've
to
covered
do.
is just software. Like I said, there is networking and other facets to this.
Yeah, we'll get into it slowly as we go along.
Yeah.
Thanks. Great, and have a great day.
Yeah. Thank you.
And bye.